Okay, this is part 2 for the alcohol. Now you have these alcohols, the isomers, the regioisomers, with different isomers, we're trying to making new functional groups and compound. And of course, you have to try to make one alcohol from others, so you can freely go back and forth and connecting various reactions. So I think we did this before, but you have a strong ionic basis, very unstable, much more unstable than the alkoxide you form as a product. But the difficulty here and the mistakes students normally get into is like they don't attack hydrogen, but they do attack the carbon. But when you have strong base and small, due to the steric around the carbon center, even it's a primary, it has hydrogens, blocking. So it's a lot easier for these small, strong bases, not selective but reactive ones, go for the greater negative charge, especially because the outcome, whether you attack for the carbon and hydrogen, the stability of the product is about the same. It's even a little more stable, the other case, but most of the time it's activation energy, kinetic region, with a less steric we talked about before. So it attacks here, and you normally get the negative oxygen that you are using to make ether. We talked about this before also. You let this one attack on alkyl halide, then you can imagine SN2, and you get the ether functional group as a product. Well, and we also talked about like the OH. You can make it better leaving group by adding electrophiles such as H+. Then you create water there, and you can have SN2 or E2, even SN1 and E1 using weak base. But there are times like this, or even bigger molecules such as nitrogen holding alkyl groups rather than hydrogens, or other bases like these. When you attempt to do some substitution and elimination with a strong base, then you need to get rid of the hydrogen and making the oxygen better leaving group. Therefore, you cannot use H+. Then you have options like a tosyl group. Here you have a toluene, methyl group, benzene, sulfonyl group with a chlorine as a leaving group for this right there. So this portion is a tosyl group, TOSYL. So this base, in the presence of a basic solvent, this can give electron to the electrophilic sulfur. You knock that out, and you are creating tosyl group. So oxygen with a tosyl group, due to the resonance ability of the sulfur oxygen. You can assume this is now a good leaving group, so you can introduce strong bases to do elimination or substitution on this. So there are other variations of phosphates, or even ATP has a phosphate in it, so you can think of that way as well. And this is sort of an activating group. Making certain functional group active. You can even use this for nitrogen leaving group. Also, in earlier video, several times we used this dehydration condition to make the double bond. So you get normally more substituted stable alkene as your major product. Here HCl is the one that we mentioned here with the H plus making hydroxide a good leaving group in the water form. Then you have a chloride as a weak base able to replace it, so you end up having substitution. Depends on the degree of the carbon that's holding OH. In this case it's a tertiary. You would have a SN1 rather than SN2, but compound with the water on the primary, you can think of SN2. Then you have a SOCl2 PBr3. So let me show you the mechanism for replacing OH. But benefit of these are generally you don't have rearrangement, while the HCl condition could give you rearrangement in the case where the OH is found on the secondary. Then when you lose the leaving group, you can form carbocation. The condition to form carbocation was that should be secondary or tertiary, or the primary with the resonance, meaning stable enough carbocation can be formed, then rearrangement is possible. But these will replace the OH on the carbon where you find the OH with the Cl from the SOCl2, or with the Br with the PBr3. So the mechanism, in order to save time, let me draw and show you in a minute. Okay, before I go more in drawing mechanism, let me show you this much first. I chose the secondary alcohol to point out the changes on the chiral center. So the lone pair of the alcohol acting as a weak base, and enough of acid is here due to the chlorine and charges induced by 3 electronegative groups on the sulfur. So you break the weak pi bond and you form this intermediate. Then you find the big plus charge and negative basic charge, and you lose leaving group. Then the chloride or the solvent will able to remove the hydrogen, and you come up with this. Then all right, so we were here. Then it could take two different paths, depends on the condition. If you don't use a solvent like the pyridine or some other ether solvent, you could have self-dissociation here, and you make the ion pair, and they don't diffuse away because they're in the solvent cage. Also, because the negative charge is present in this side of the molecule, nothing is actually migrating, so no rearrangement usually. So while it stays like this briefly inside of the cage, the base is attacking the acidic carbon, and this breaks up, but it comes back down. Then the chloride breaks off and attacks from the same face where the thionyl chloride unit was. So the stereochemistry is actually same. So retention, spell retention of configuration, but the mechanism is like SN2, but we call it SNI because the thing, arrow pushing and the electron attacking happen internally. So SNI, and stereochemistry is with the retention. But when you have a basic solvent, the solvent prefer attacking sulfur and break and reform and kicking out the chloride, then you form this intermediate. Nitrogen is now positive. So you can see the chloride is coming around, attacking like a backside attack in SN2. You break that off, but you can see this go further and make a CO2, and the pyridine can be released, and your chloride sitting on the carbon with no rearrangement again. And also the stereochemistry, unlike the previous case, it is now inversion. But I can give you another example of thionyl chloride replacing the alcohol. This one is a short, so let me just do it. Let's make up something like this, and the SOCl2. No basic solvent, so you expect this to be SNI, right? So the same thing happens, and you get sulfoxide with a chlorine. When they break off, okay, you form primary carbocation, but that's good enough because you have resonance going on. So SN1 style is okay to lose unimolecular reaction taking place here. Then in the solvent cage, they stay like this, but when they break apart, the chlorine is now attacking there to push electron here. Or you can think of it as they could have a resonance. So you can see positive charge moving to the more substituted carbon, and that moment you can see the partial positive developing there in the resonance. So the chlorine is able to attack there better. So you get product. It looks like that it had rearrangement. Before I show you the other example, I need to correct some mistake I made. This actually is not carbon dioxide. As you can see, this is a sulfur. And also, I just realized right after this, thanks to this example, I realized the mistake before. So this is a sulfur. And you can think of this kind of example too. Let's put some more carbon to make the molecule asymmetric. So if they give you the product, something like that, and then ask you to show the mechanism, then you need to apply this mechanism. But to show this better, I have to show you the sort of transitional state. Then you have sulfur, and the sulfur still has a lone pair as a sp3 hybridized sulfur. We talked about this before, like this. Then you can see the chlorine is already close to this. So as this break off, you can form SO2 stable gas, and then this gains electron to the chlorine, but it can donate it to the double bond, and double bond can push off, and this concerted mechanism is favored, and you can get this. Okay, so you can replace the OH without rearrangement. You can put chlorines, you can put BRs. Yeah, so the basic oxygen, very weak but basic, able to attack the acidic phosphorus with the 3 leaving groups and develop the positive charge and donates and kick out the bromine. Then you form this intermediate with a positive on the oxygen, a very acidic and good leaving group. So the bromide is able to do backside attack just like SN2. So there is no rearrangement, and you're gonna have a replacement, and the product is formed there with the substitution. All right, next, in this big scheme, we have a little section of oxidation. Let me talk about that. So I hope you can recall that the alkene is formed from the alkane. So you actually go through the bromination and the alcohol, right? Then you reached here, each step you have oxidation, and you have over here the carbon actually being oxidized by losing hydrogens. So further oxidation can give you diol or the alcohol on the secondary or tertiary. So you could make that. And we talked about different more steps of oxidation, giving different oxidation on this carbon. So then further oxidizing alcohol, the secondary one, you go to the ketone. But if you oxidize the primary, you can go to aldehyde or further to the carboxylic acid. That earlier I mentioned that this step can be done by weak oxidant, but the second step only can be done by a strong one, meaning this can also be done by a strong, very reactive oxidants. So if you know who are the weak or strong ones, you know what to form as a product. So if I change the paper, here are some examples of strong and weak ones. The strong one, the chromic acid is representative, and the weak one, you can say PCC and PDC. Those are also chromic acid form, but in a weak form. And the sworn oxidation is using DMSO sulfur compound as oxidant. So let me show you the mechanism of it. But this basically means if you put PCC here, then you get this. If you put chromic acid, you get this. For this primary alcohol, if you put sworn oxidation condition, then you don't get here. You form this as a product. And if you put chromic acid, you go all the way to this product. So with that in mind, let me just show you the mechanism. Then we'll be done with the oxidation. So that's what we are talking about. Strong, weak, strong, and the weak difference because of the degree of the alcohol. The chromic acids are given in different form. the strong chromic acid, not PCC, PDC, weak one, they can give you this reagent in variety of forms. The real active form of the chromic acid looks very like sulfuric acid, like this. Instead of sulfur, you have a chromium, and this one has a +6 oxidation state, so very much electron hunger. That's why it is acting as an oxidant. It is able to take away electron from the alcohol, but itself is gaining electrons, so it is getting reduced, I said. This can be given like this, or K2CrO4 with the H2SO4, sometimes sodium or potassium bichromate with the H2SO4. There are more varieties, but you know, I hope when you see these things, if you think about it, you know, when you react with them, you come up with the H2CrO4, right? So same thing. And I'm hoping that I don't have to, I'm expecting you come up with a simple chemical reaction by now. So there you have a sulfuric acid donating 2 hydrogens, so the negative oxygens here will get the hydrogen each, and you get chromic acid. This bichromic acid, you have 7 oxygens, so you have 3, 4, 5, 6, 7, K, and the K, right? So 2 hydrogens going here and here, and then sulfuric acid certainly had some water in it, so water reacts with them and split, so 1 more oxygen from water gets there, then you have 4 oxygens with the hydrogen. The water had 2 hydrogens, so one of them can go to here, react with this base you are forming, so you get the 2 chromic acid. So whichever way they give, I hope you can deduce that as a chromic acid right here, so I can show you the reaction. Let me show you the mechanism with a primary alcohol. And there you have a variety of mechanism possible. So first, you can think of ways of attacking here, and you break the pi bond. That's because, again, the alcohol is basic, then chromium is very acidic. Then you can think of the solvent taking this hydrogen, and this oxygen taking the hydrogen from the solvent. So long story short, you can imagine this. Then water molecule come along. You know, due to the resonance here, this oxygen is acting as a good leaving group, so water can certainly think of replacing it. So you attack here, you replace. Then you can imagine the product will be similar to the reactant, right? So you are basically using water and doing SN2. you're going backward. So that equilibrium is pre-existing. Then what other acid you see here? Due to the big time positive charge on the chromium, you can imagine these alpha hydrogen more than the beta hydrogen in the elimination, right? These alpha hydrogens are highly positive next to the carbon. So this can attack on the alpha hydrogen. And I hope, remember we did this. When we do oxidation of alcohol, you're losing hydrogen, gaining extra bond with oxygen. So gaining extra bond with oxygen, and you get aldehyde. That's one mechanism getting there. What if this base attack the hydrogen then? Okay, let me use the blue arrow. So you know this is a blue arrow. This is a red arrow. So if you do that, you are breaking this off and you are making a good leaving group with this conjugate base formed. By the way, you know what the hybridization of the chromium here, right? We talked about that. So anyway, without telling you the answer about the hybridization, let's focus on the mechanism. So this one is a base. You have a good leaving group, and you're looking at the alpha carbon because it's the most positive and the least sterically hindered there. And you go try and do SN2, and you see no problem. Then as soon as you do that, you are looking at this intermediate. This can actually work internally. This as well. One of the oxygens can react with a hydrogen. You can count 1, 2, 3, 4, 5. So 5 atoms apart in the three-dimensional structure, they can get quite close. If you imagine the rotation, you can imagine three-dimensional distance between the hydrogen and some of the oxygens. Here also that could happen, but what can also happen is because the water is abundant as a solvent, again, this is a good leaving group with the resonance, so you can attack on the alpha carbon and kick that out, and you go back. So the reaction is reversible and you can go back always. However, also like a previous case, oxygen of water can attack on the alpha hydrogen and you break this off. I want to revisit these two mechanisms, and I want to say they are E2 kind of mechanism. I hope you remember the E2 is when you have hydrogen on the beta and the leaving group on the alpha, some base attacks, and you form double bond. Due to that electron, you kick out the leaving group and you form double bond, right? So here, you attack hydrogen. It was alpha hydrogen, but doesn't matter. You attack hydrogen and you form double bond. It's not the carbon oxygen instead here. It's like it's oxygen here, but doesn't matter if it's oxygen, it's still E2. So oxygen is forming double bond and then you're losing the leaving group right here. So it's E2 here as well. This alpha hydrogen attacked by the electron donor, forming double bond, you're losing hydrogen, and you also lose leaving group. So it's kind of E2, right? So E2 like reaction. So you are still forming aldehyde out of this. So with aldehyde, if you have a PCC and the PDC or sworn reagents, you cannot react anymore. But when you have a stronger oxidant like this chromic acid, you still react. There could be also a couple different mechanisms, but I want to make it clear. as an undergrad student, you don't have to know really exact, correct, proven mechanism. If you can come up with a reasonable mechanism, it should be okay. In order to cross out some of the proposed good mechanisms, you need to conduct the experiment. Even for the professional chemist, you cannot predict the mechanism precisely. Even when you do some quantum mechanical calculation, you know, which is more strict thinking than our mental thinking, it's difficult to come up with the right answer. You need to actually run experiment. So your goal is, you know, being able to come up with a reasonable mechanism. So I'm suggesting you to feel free to come up with your own mechanism and see you are not making any step impossible. So here you can say, you know, you can attack there and go from there, or you can say, I want to attack hydrogen just like a sulfuric acid. Then you form this. Then this can, as you can see, attack there, because resonance will give oxygen neutral but carbon positive charge. So you can certainly do that. And it is still forming somewhat reasonably stable product. So here, again, internally one of the negative oxygen can react, or you can use a solvent to get rid of the beta hydrogen, because it is positive, except the carbon, that's the most positive one. So you've seen before, you can attack here and you go for the E2 type of mechanism, and there goes leaving group. So this is the moment chromic acid once again is getting reduced. It is receiving electron. So you get double bond oxygen and the OH, you got the carboxylic acid. Okay, my goal is not to make the video too long. So PCC and PDC, the reagent is a chromium based reagent, but it's weak. So you can imagine the mechanism similar to the chromic acid. But sworn oxidation is completely different, so I will show you the mechanism. And also, to save time, let me pause. Okay, here. So the primary alcohol with a weak condition, like a sworn oxidation, you're supposed to stop at aldehyde. So first, this oxalyl chloride react with the DMSO, because DMSO's double bond here is weak. That's because of the size difference. Sulfur is too big for the oxygen, so this d orbital is not forming good pi bond with a little p orbital of oxygen. So you have sulfur becoming positive, oxygen become negative. This oxygen negative is able to attack here and the break, reform, and kick out the chlorine, and you have this. Then because this is a good leaving group, the chloride can attack and replace, and that acts as a leaving group. Actually, the mechanism is not stepwise like this, but that's okay. If it's not stepwise, it is going to form double bond already here. Okay, so this will form double bond, then you lose a CO2 gas, the electron goes to the carbon and you make a carbon monoxide and you lose the chloride. So you have a chloride sitting around here in the product. Then the sulfur still Lewis acidic, so oxygen, the alcohol finally react. Then you lose chlorine. Then here you form the product but not quite stable yet, so you need a base. So the base, the bulky base, will attack the hydrogen like elimination. You attack hydrogen and give electron to the carbon and it becomes carbanion. The carbanion is stable because the sulfur is positive. So this kind of complex is called ylide, and you'll see more ylide later on in the reaction, like a Wittig reaction. You can have a nitrogen ylide, a sulfur ylide, and phosphorus ylide, and all kinds. Anyway, this carbanion is stable because the sulfur's MTD orbital is able to accommodate some of the electron density here. A sort of resonance, so you can think of the partial double bond here. So the carbanions stable enough. Then this one internally, like we've been talking about it in the oxidation, attack the beta hydrogen right there, which is alpha hydrogen from the alcohol functional group, but it's acting as a beta hydrogen in E2. That's what I meant. So the lone pair here is attacking hydrogen and forming double bond, and reduces sulfur. So you form methyl disulfide as a neutral molecule, and on this side you have the aldehyde, and the reaction will be done. Okay, back to the big picture. So you can fill in this box using strong or weak from the secondary or primary. Then how do you make ether? Ether will be something like you have oxygen bound to whatever other groups. So it's better to have the R group primary. Okay, if it goes to the secondary and tertiary, then you may look at the elimination. So not a good strategy. Assuming this part is a primary, this is straightforward, right? This as a weak base, you can make it alkoxide using some of these strong bases. So you get the alcohol negative. Then you can aim like a primary alkyl halide to do SN2, and you replaces it, and you get this ether, asymmetrical ether. Then you have your Williamson ether synthesis. This is always compared with the acidic condition. If you put H plus, you can always form good leaving group. Another mole of the alcohol, you can imagine. Then this can attack and lose leaving group. Then you can lose hydrogen here with the water, so that step skipped, and you can have symmetrical ether. So that is the useful one. But when you make an asymmetric ether, Williamson ether synthesis is favored. That's because if you attempt to react with the simple alcohol and this in the acidic condition, then you can come up with the 3,4 products. such as this becomes a good leaving group and that attacks, or that becomes a good leaving group and this attacks, or this becomes a good leaving group with the acid and the same guy attacks, and this becomes a leaving group and the other guy attacks. So you can have 4 different mechanisms, but 2 of them are same, so you expect 3 products. Messy reaction, so not recommended for acidic condition in order to form asymmetric ether. So that's why Williamson ether synthesis is favored. But if you don't do Williamson ether synthesis, you can say, what about I have alkyl halide, that's a tertiary, okay? SN2 is not good because it's doing E2, but if you have a tertiary alkyl halide here, that's a tertiary. If you heat up, you lose the leaving group, that will be stable tertiary carbocation. Then you put your alcohol and you can do SN1 type of ether, asymmetric ether synthesis. That's not Williamson, but you can still do it. So forming asymmetric ether, you can do with a primary or secondary, tertiary in different condition. So one application we can think of before we stop, the alcohol can be converted to the ester. We talked about it before, but if you can retrosynthetically figure out where to disconnect, either here or here, it doesn't matter, either way it works. But let me cut there. Then you have this piece right there, and this piece will be your reactant. You need a leaving group, so you can do simple reaction and you come up with ester. But you know, you learned in previous chemistry classes in high school or Gen Chem, you can make ester using acid. So carboxylic acid with the alcohol and the catalyst, you can form this. So Fischer Esterification. This is something we'll do later in detail mechanism, but you need to know you can form this. So we have to wait until we cover carboxylic acid functional group to see the detail mechanism. But I hope you are getting the concept of multi-step synthesis and you study around the functional group. And this was a part 2 of the alcohol, and I'll see you next time with a more different variety of a functional group. Bye.